Well, as you can see on the screen, we have a talk by Chuck, W1HIS, improving your received SNR. It's been a while since we've heard from Chuck. Some of his very first learnings on how to improve your SNR, signal to noise ratio. He presented to our club back many years ago. You can still find some of his work up on our website. This would represent an update to that, a review and an update. Chuck has been a YCCC member since 2003 and a ham since 1956 when I was 2 years old. Um, so, as you can see, Chuck has been involved with MIT as both a student and a faculty member there since 1969. Wow. All right. With that, Chuck, are you ready to share your presentation?
Yes, sure. All right. So you're looking at my whole screen, and one thing I noticed, I sent Ken asked for a photograph of me, and it was a great photo. It was taken by W01I as opposed to W01N.
Yeah.
And I thought it was a wonderful photo. And obviously, Ken disagreed because he put a photo, I don't know where he got it from. Um, that was me uh, operating in a field location in a contest. And I won that contest, number one. um, but that's not what I thought was a good picture. Here's the good picture. Uh, I'll put it on my screen so you can see it. Now, see this? This is the picture I sent Ken. And you see me in the picture?
Well,
Everybody see me?
took me about 10 minutes to find you, but yeah.
Okay, I'll show you where I am. To make it easy, let me zoom in a bit. See me now, right here?
Oh,
There you are.
Okay, now,
Holding on for
what?
dear life, it looks like.
Well, no, no. You see, I'm no, I'm wearing a full OSHA, safety harness with fall arrest and all that. See this lanyard that goes around the tree? That's for the fall arrest harness. And this picture is relevant for today's. Um, Let me make that picture smaller. It's relevant for today's presentation because it makes the point that I don't have a tower. I've never had a tower. I have wire antennas that are stretched between trees. Now, so I do a lot of climbing, but I don't climb. I climb other hams towers and help them with their antennas. Uh, but for my own antennas, I climb trees. And typically, to climb a tree, this is antenna. This tree here was holding up one end of my antenna for 20 years. Um, and first, I put an extension ladder up as high as it'll reach, and it's about 20 feet, nominally a 28-foot extension ladder. And then I start installing steps in the tree so I can run up the tree fast in the future. And if you look very carefully, look, see this thing right here sticking out of the tree on the right? That's a bolt with a head on the end. As I go up the tree, I use a handheld drill. I drill these are half-inch bolts or 5/8 bolts. I drill a hole in the tree of that size, and I stuff the bolt into the hole, quickly tap it in a little with a hammer. Um, you have to do fast because the tree bleeds and its sap will very quickly glue that bolt in so it'll never come out again. And I install steps, one side, other side, back and forth up the tree. One side, other side, until I get up to, way up here. And here, off beyond the top of the picture, I've got a pulley up there and ropes and so on that supports the antenna. So this antenna was my antenna for 20 years or so at that particular QTH. It was a sloper, it was a wire sloper, and its center was 30 feet above ground, 30. Now, in contests, it was 30 feet centered above ground, and the length of the sloper from one end to the other was 70 feet, 70. So you can see I could get a half-wave dipole in there for 40 meters. And for 80 meters, this dipole was electrically short. It was only half as long as it should be. And for 160 meters, it was a quarter of a dipole length. So it, getting much efficiency out of an antenna that short is not easy. And the dipole is not only is it too short, but it's also too low and close to the ground. But the worst thing about this antenna was its QTH, and I'll get to that. I'm going to jump around in this outline. Okay, here's my QTH. Wait a minute, let's see. Let's try that. Okay, this is an aerial photograph of the greater Boston area. Here's downtown Boston down here, and here's the Charles River, here's the harbor, here's the Mystic River Bridge right here. And all of this area for miles, off the top and off the bottom, is solidly built up. And a lot of it is industrial, a lot of it is commercial, a lot of it is housing, but it's very densely built up. In this photograph, you cannot see individual buildings, you just see all this. Now, all of those buildings are generating QRN, that is radio noise. And your received noise environment in this area is very high, and this is the reason why there are no contest stations in this area. There are contesters who might live in this area, but they're not going to win any contests operating a station in this area because you can't hear anything. The noise is awful. So guys like that, they operate other stations, K1TTT or whatever, stations that are out in the country, away from all this noise. Now here's right there, that plus sign right there where the cursor's moving around. That's my station right there. And so you see I'm embedded in this, and this map is solid build up off screen, off side to the left, and off the top and off the bottom. This is a just terrible noise area. Can anybody think of a contest station inside Route 128? Can anybody speak up or raise your hand or something?
I'm not aware of any.
Okay, W1DYJ. live in Woburn. Woburn is mostly outside 128. You outside 128?
I'm actually inside by a mile.
Okay. So, uh, so you are one contest station inside 128. Can you hear?
AK1MD.
Where's that? What was that? AK1MD. Oh, Alex? Uh,
He's in Newton.
yes, yes, you're in Newton, and yes, that's right. You're in the middle of this. You're way off here on the left out here.
He's south
Um,
of Route 9.
yeah, that's right. I know where you are, but this you're a little bit off screen here. Um, how's your received noise level there, Alex? AK1MD.
That
Hello.
was Chuck. It was Fred K1VR saying that, and his noise level is relatively high, but he works really hard at it, including using a phasing system and a noise antenna.
Okay, that's a good idea. He does very well. He's a good operator. Fred's own station is outside 128 in Lincoln, and it's a great station, and a lot of good operators, including Fred, work there. Okay, it's hard to hear if you um let me get rid of this. Okay, that's why you don't find many contesters operating stations inside 128. Well, I was inside 128, as you saw in that picture, and my noise level was awful. So I I made a project of reducing my received noise level. And as I'll show you here, I reduced my received noise level so that it was the same as the received noise level of stations in very rural western Maine. And I'll show you where some of those are. Here's one of the stations. Uh, okay, you see that little dot right there in the center? That's the station. That's W1IMD. And I operated that station remotely via the internet in a whole bunch of contests. Um, and mostly I did it with one other operator, and we split shifts. He'd work one shift and I worked the next shift, and so on throughout the contest. That other operator was K1ESE, who's a very good operator, much better than I am. Anyway, here's where that station was. I had to draw a red circle around it because you wouldn't see it on the map. This is all woods. The scale down here in the lower right, you can see it. It's a 2,000-foot scale right there. So he had, there's a long distance between that station and any noise sources. Basically, the noise sources are down here and here. And I reduced my received noise level in Belmont, Mass, in the middle of the Boston mess, to the same as this station. And I'll show you how I did that. Well, I'll show you how do I know. But let's get back to, let's see if I can get this picture out of here. The other station that I'm going to compare with, I just mentioned K1ESE. Okay, there's his station right there. It's a street address, 30 Main Route 35. And you notice there's not much noise around him either. Now, I operated W1IMD and also K1ESE remotely via the internet. So via the internet and A to D converters and all that stuff, I was able to control the receivers and hear exactly the same audio that I would have heard if I were sitting there at the station. And now to compare the noise level there, let me see, let me find my picture. Is this the picture? Well, I'll come back to that. I'm going to jump around here. Oh, local and remote. Okay, this is my shack in Belmont, Massachusetts. And I have a station there with this, antenna is centered 30 feet above ground and it's too short. And I operate that station in contests. And to operate that station, I sit over here in the corner. My K3 is hit here. There it is right there. It's almost completely hidden right there. And there's its pan adapter. There's its keyer, microham keyer, antenna tuner, and so on. And I can also, by sitting in the other chair or moving my chair, I can operate K1ESE or W1IMD in Maine. And I'm doing it in this picture. I'm connected by the internet, and these two monitors on the right are driven by the station computer up in Maine. And so I could swivel back and forth, or I could, put one of the main station in one ear and my Boston area station in the other ear. So to compare my received noise level to one of those stations in Maine, I would select either my station or the main station, and I would turn the knob until I found a weak DX station that was about at the noise level. When I found that station, let's say I found it with my own station on the left here, then I would reach over to the right and I would tune the station in Maine to the same frequency and listen to the same station. And I could compare the signal to noise ratio in Maine to my signal to noise ratio here. And I'd make a note, this one's better or that one's better. And then, having started by choosing a station in my local station, choosing a DX station that I heard at my local station, then I would switch to the main station over here, and I would turn the knob or physically through the internet, and I would find a weak DX station just at the noise level. And then I would go to my local station and tune to the same frequency and hear that same station at my station. And then I went back and forth between the two, finding a station with one station's receiver, and then comparing the signal to noise ratio at the other station. And this was unbiased because I alternated all the way. And sometimes the station would be better, had better SNR in Maine, and sometimes the SNR was better at my station in the Boston area. But on average, they were the same. In other words, half of the time I could hear the station better in Boston, and half of the time I could hear the same station better in Maine. Now, I thought that was pretty impressive because conventional wisdom is that the noise level is higher in the city. And conventional wisdom is not based on somebody's gut feeling, but there have been quantitative surveys of radio noise level done by the government because it's a very expensive proposition. And the government surveys of signal to noise ratio are published. Now there's let me back this down a little bit. And okay, this is good enough. One publication that's relevant here is a book entitled Signal to Noise Predictions Using VOA Cap. You've all heard of VOA Cap. That's the program or the software or the website that you use to get propagation predictions. And that program actually predicts received signal to noise ratios. And in that book, it's a reputable book by a reputable guy and a reputable source. It's published by Rockwell Collins. Collins is the same Collins as Collins Radio. They were bought by Rockwell. And this guy, George Lane, knew his stuff. And the government survey involved flying small planes with receivers and antennas all around, close to the ground, and measuring noise levels. And that's a lot of data from a lot of places, but a summary of the predicted noise level is published in this book for three kinds of areas. One is quiet rural locations. That's like those stations up in Maine. It's about as quiet as you'll find, within short of traveling way up to the Arctic Circle or something. That's quiet rural. Then there's rural. Most of the contest stations we're familiar with are rural. They're not all built up like the area, the Boston area. There's stations like K1TTT, KC1XX, etc. And another area that they computed numbers for are so-called residential areas. That's like where I live. In other words, not exactly urban, not downtown, but like Belmont, where I live. And this is done, the government survey was done with a spectrum analyzer, and it swept the whole range of frequencies. But here I'm reporting the survey results for the 6 HF contest bands, one of which is 160 meters, which is not HF, but it's a contest band. And you can summarize this fairly simply. One is, and everybody knows, the noisiest of all these bands is 160 meters. See this? Minus 139 dB with respect to a 1 watt per hertz bandwidth. And the quietest band is 10 meters. We all know that it goes that way. And the other trend, which is simple, is that in a residential area, like say Belmont, the noise level is around 20 dB higher than in a quiet rural area. For example, here 139 and 150 at 19 dB, 19 dB, out here 20 dB. So in round numbers, in Belmont, my noise level should be about 20 dB higher than the stations in Maine. Well, I'm professionally, I'm a scientist, and so I measure things and I do experiments. And I did the work to calibrate my station so that I could measure received noise level in dBs with respect to 1 watt per hertz of bandwidth. And so where do my measured results fall relative to that survey? Okay, let's go. Let's see. Oops, gotta make this big. Keep forgetting which. Okay, here we go. So this is the same table you just saw, but there's one additional row in here. This one here, W1HIS, and these are actual measurements calibrated. How do you calibrate? That's a long story. Well, you can summarize my measurements pretty well. My house is about 4 dB more noisy than the government survey in 1980. Here, 4 dB here, 4 dB here, 3 dB here, 4 dB here, 3 dB, and 4 dB. So why is my location 4 dB higher than the survey? Well, I think it's pretty obvious. The survey, the government survey, was done in 1980. That's before every single house contained 100 switching power supplies. In your house, you probably have 100 switching power supplies. And you're probably going to say, that's ridiculous. It's not ridiculous. I could go through your house and I could point them out to you. They will be the charger, all the chargers for your cell phones. They're all switching power supplies. The switching power supply or charger for your laptop computer. The much bigger switching power supply for your desktop computer. Then nowadays, your house has LED lights everywhere, right? No, not incandescent lights. Well, in 1980, your lights were incandescent and they don't make noise. But every single LED light, just in this room I'm sitting, there must be 15, LED lights. You can with a receiver, you can measure, you can see they all generate radio noise. So, and some sources are spectacularly big. For example, nowadays, a lot of appliances like dishwasher, washing machine, clothes dryer, exercise treadmill, lots of appliances have variable speed motors. Once upon a time, a washing machine had a fixed speed conventional induction motor that was built for 60 hertz AC. And when you wanted the drum of the washer to spin faster during the spin cycle, a mechanical gear change was made. That's how you got the other speed. Well, nowadays, it's cheaper to do it with electronics. So a modern dishwasher, for example, or washing machine has a variable speed motor. It's a three-phase AC motor that's driven with three-phase AC power of variable frequency. Now, a three-phase motor rotates at the frequency of the current in the field windings. And so when in order to vary the speed of the motor, you change the frequency. Well, there's a switching power supply that's generating a very rectangular waveform because it just switches to drive the three phases of that motor. And nowadays, air conditioners, all kinds of refrigeration machinery have variable speed motors on it. So it's amazing that my measurements were only 4 dB higher. But let's leave it that it's still true that my location should be about 20 dB more noisy than the rural stations in Maine. And it was, in fact, it was much worse until I made a project of reducing my received noise level. And I reduced my received noise level by 30 dB. Maybe the first 10 dB of that was easy because, if I find the three noisiest things in my house or in my neighborhood and just silence them, right away I've dropped 10 dB. That last 20 dB requires some effort. Stations like Tim Duffy's K3LR, they have those winning contest stations have already done what I did. Tim Duffy came to a YCCC meeting actually 20 years ago when I talked about how to reduce your received noise level. And he was inspired, and he and I had various conversations and email exchanges and so on. And he wound up doing what I said to do to reduce his level. And all the big contest stations like KC1XX, same story there, where John Kaufman, who was the 80-meter CW, 80-meter operator there, he was my agent who did all the noise reduction at KC1XX. The big contest stations have already done what I teach, so this talk won't help them. They've already done it. This talk should help you if you're, a mere mortal, like, the guys who just joined in this meeting, because if you're a mere mortal, chances are your received noise level can be reduced by 20 to 30 dB. And that makes an amazing difference. Obviously, you can't hear them. You can't work them if you can't hear them. And before I did this noise reduction, there were all these stations out there that I couldn't hear. In fact, I remember receiving email from DX stations. There's a YCCC member, I can't remember now who it was, who traveled down to ZL territory, that is New Zealand, for one of the big contests. I think it was CQ Worldwide DX CW, to operate at a superstation down there that had, towers and wires and rhombics and everything. Because it used to be a commercial telecommunications station that was closed, and somehow Hams managed to take it over. So they had a fantastic station. And the YCCC member who went down there sent me an email after the contest and basically he says, "What's the matter with you? I heard you calling CQ and you were really loud, and I called you and I called you and I called you and you never answered me." And I said, which is true, "I never heard you. Of course I would have answered you, you know, for the mult, even if you weren't a YCCC member." And, but I couldn't hear. And if you haven't done what I am about to advocate, you can't hear. Now, there is a lot of material. There's so much material. Uh, there's so much to learn about how to reduce your noise level that I cannot and I won't try to cover it in this talk here. I have put 100 megabytes, see this? 100 megabytes of tutorial material. I gave it to Ken, WO1N, and he said he'd put it on the YCCC website for everybody to get. I looked at the YCCC website before 9 o'clock today, and I couldn't find it. Ken, if you're still here, do you know, is it up yet?
No, it's not up yet.
Okay. I put the material up at my own OneDrive area, my own personal OneDrive area, and if all else fails, I will post a link for everybody to the YCCC email list, and you can get it from download it. And there's a lot of information here, and all I'm going to do here is give you a sort of a table of contents of what's there, and you can read the parts that interest you and so on. And everything you need to know should be there. What do you need to know? How to receive your noise level. I'll give you the table of contents here. Basically, you've got to find where your noise sources are. For example, I just mentioned a few, like any machine that has a variable speed AC motor. That's a killer. That's big because these motors, you know, HVAC or washing machine appliances or something like that, these motors are big and they draw a lot of amps, and that's being switched. And not only that, it's an inductive load. It's just awful. And so, but the really big ones are easy to find, and you can predict what they're going to be even before you measure them. I need to get this. I just screwed up my screen sharing or something. Just a minute. Okay, I'm back. But once you've killed the easy things, you've still got 20 dB or so to go. And I'm going to tell you how you can find every one of them. In your house, you may have dozens that are loud enough to be heard in the ham bands, and you can go. I'll show you how do you find them, and the first ones you find will be the strongest noise sources, the worst noise sources, and once you silence them, then there's this whole layer, you know, right under them that now you can hear because they're not masked by the strong sources. And so then you have to kill them. How do you kill them? I'll tell you exactly how. So here's the table of contents. Let me see. Oh, I just wanted to I just want to show you 3 slides basically to give you a reason. Why should you believe me? There's a lot of snake oil sold in this business. You know, there are lots of companies selling filters and common mode chokes. And some of the filters are very good, but you need both filters and common mode chokes. Most of the commercially available common mode chokes that you can buy from, you know, all the vendors, you know, the usual vendors, they are not worth your money. And that's a strong statement, and people didn't believe me until I showed them. For example, I mentioned W1IMD in Western Maine. He has a very nice station. I made it nicer. I reduced its received noise level. He had bought some expensive common mode chokes from, I'll tell the truth because it's true. What's Tim Duffy's company called? DX Engineering? Okay. He bought them from DX Engineering, and he'd take them out of the box and it looks very professional. It's a nice box and a nice label and all that. And that's what W1IMD was using. And when I saw that, I had separately measured chokes like that, and I knew they were crap. So W1IMD had some sophisticated instrumentation, and so we used his instrumentation, and I measured him, and I showed them that they're crap. I mean, they're I'll skip the numbers, but you shouldn't use them. They're a waste of money. So, armed with the measurement results, W1IMD contacted Tim Duffy and said, basically, there's this guy here who says your chokes are crap, and here's the measurement, here are the data. And bottom line, W1IMD returned those chokes to DX Engineering, and Tim Duffy gave him his money back. Duffy did not contest my measurements. And I've looked at a lot of commercial chokes. They're no good. So one of the things that I'll show you in the materials that I've put on the web is so how to make your own choke for not much money, and make it on your kitchen table, and it'll cost you $10 to $20 in materials. The main material cost is ferrite and coax and connectors for the coax. And then you've got to package it somehow. And it may not even be necessary to package it because ferrite is waterproof and coax is waterproof. And so you don't really even need to package it. My own chokes at my own present station are not packaged, and they're fine. But you can make for $10 or $20. You can make a good choke that is much better than what you can buy for $200. And I'll show you how to do that. And I'll tell you here where to buy the ferrite, what type and part number ferrite, and and so on. It's really easy. So, all right. I don't know where this, I seem to be accidentally drawing lines on my, all right. So, but another question is, should you believe me or should you believe the vendors of crap? They've got big budgets and very slick web pages and make really nice stuff. And I don't have anything. And should you do what I say? Well, one way to tell, I don't know how to get rid of this pencil. Let's see what this does. Okay. I've told you that I've compared tests. Okay, but maybe I'm lying too, because everybody else lies. One way you can tell is you can look at my contest scores and compare those to other stations. One of them I mentioned is K1ESE. I got to figure out how to get rid of this. I seem to be drawing tools here. All right, I'm back. Okay, here's one comparison from I want to compare with K1ESE, was one of the stations I showed you. This is the New England QSO party. I'm going to get to some other contests, but in that contest, I had another operator, somebody assisting me at my station. So I entered multi-single category. Anyway, I made, this many 592 QSOs and had a score of, in round numbers, 92,000. How about K1ESE right here, down here? He was single operator, high power, and he made almost as many QSOs. I had 592, he had 559. And his score was less than mine. No, not a lot less, but I did it inside Route 128, in a noisy location, and he did it in a quiet rural area. Now, here's another kind of contest. Remember, I showed you, and you already know, that the noisiest band of all is 160 meters. So if what I tell you to do matters, it should matter more on 160 than any other band. This is 2015. This is the ARRL 160 meter contest. Remember, it's a 160 meter contest, and my antenna is wire. It's 30 feet above ground, and it's only 70 feet long. Okay, that's not how to make an efficient antenna. I have no ground system, no ground plane, no radials, but I finished first in single operator unlimited high power in Eastern Mass. And there, it's a bunch of respectable stations in Eastern Mass. And, they've got towers with, 100 radials and all this stuff. Why did I do so well? It's because I could hear stations on 160 meters that other people couldn't hear. That was 2015. I did it again the next year, 2016. Oops. 2016, 160 meter contest. First place, single operator, unlimited high power, Eastern Mass. And that includes, stations in the outer suburbs that are a lot quieter, like say K1IR. There are a lot of stations in Eastern Mass, including probably half of you. Once again, with this pathetic antenna, I won first place in Eastern Mass because I could hear stations that others couldn't hear. Let's see if I can. Okay, so I hope I have some credibility. Now, this is just a table of contents for how you can reduce your received level and an outline. This is a sort of table of contents. It's pretty straightforward. First step, you have to find the noise source. So I've got a bunch of pictures and a bunch of text about how to find the noise source. You can walk right to it. It's not hard to find noise sources if you know how to do it. It is hard if you don't know how to do it. And I've been contacted by a bunch of hams in the YCCC who, including guys like Mark Pride, what's his call?
K1RX.
Yeah. All right, that sounds good. He's an example, but I've gotten a dozen or two calls from YCCC members, and they said, I got this horrible QRM on 80 meters. I can't hear anything. It's awful. And I went and I did this and that to find where it was, and somehow it's not there. That's because you have to know how to find them. And I've got a few pages of text and drawings and photographs and so on here about how to find a noise source, starting with I'm in my shack and I can hear it in my receiver. And to identify the source, and the source is, maybe at a neighbor's house a block away. And another example, that's enough. The first step in finding a noise source is to characterize the noise. What does it sound like? How does it behave? When does it start? When does it stop? Actually, you can deduce a lot just by that. An example being, I had a terrible noise source come on at my house. This is after I had quieted down everything, and I had a really low noise level, and then this awful noise came on, and I heard it again the next day, and I heard it again the next day. That's because I had a skid with another ham, CW skid on 80 meters, and had it at from 5 to 6 p.m. In the afternoon, something like 5 days a week. And it seemed like every day at 5 o'clock, or very shortly after 5, this horrible noise would come on. And one clue is just the time of day. When does it come on? Well, what happens a little after 5? People get home from work. And that gave me a clue that somebody in my neighborhood is coming home from work and turning on something. what would they turn on? Well, maybe the washing machine, and characterize the noise. What's it sound like? Well, it sounded kind of like and periodic like that. And so I thought, washing machine. Okay, as it rotates and the clothes go flopping around the drum, the load on the motor changes, and so on. So I thought somebody comes home and starts the laundry. So now, how to find them? Well, I used a technique that I describe in here of radio direction finding, which is really easy. I'll show you in a picture. And the next afternoon, at 5 o'clock in the afternoon, I was ready. And I had my portable radio direction finder that I could walk around with. And I was all ready. I had it all out, set up, tuned to 80 meters. And it was by the door, so I could just go right out the door with it and start around the neighborhood. So I live on this street, so right away I walked up the street that way and the noise got softer, and I walked down the street this way, the noise got louder. And at this point I say, okay, let's go that way. And I used the direction finder now as I walked up the street. As I walked up the street, houses on both sides, I was walking past a house on the right and a house on the left. Well, my direction finder says, no, it's ahead of me. It's farther up the street. And I got to a point where if I kept walking, then it got less loud. Aha, I've just walked past the house. That's it, it's in. So I walked back to where it was the noisiest. So it must be that house on the left or that house on the right. And so with my direction finder, I probably just walked. I walked onto the lawn of the house on the right, and I walked onto the lawn of the house on the left. Okay, it's noisier of the house in the house on the right, and so on. Then I rang the doorbell, and I met the woman who lived there, and told her that I was hearing this radio noise from her place. Now, I really ought to write a few more pages about how to deal with neighbors, but I can't do everything right now. And so I said I suspected that it might be her washing machine. Does she do laundry when she comes home? No. Well, one thing led to another. She had an exercise treadmill in her basement. She would take off her office clothes and put on her sweaty clothes and get on the treadmill. And as she walked on the treadmill, every time she put a foot down, that changed the load on the treadmill motor. And that explained why the noise went ooma, 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 ooma. This is, feet coming down on the treadmill. So now I knew, okay, it was the variable speed motor in that treadmill, and I knew exactly what to do that was non-invasive, and I did it, and I never heard that treadmill again. And a few years later, my doorbell rang, and it was the woman at the door, and she was giving me back my fix that I had left there, because she says she'd thrown out that treadmill because it was a piece of junk. Once you find the noise source, then what you have to do is keep the noise that's generated by the source from getting onto wires or cables that are long enough to radiate. The device itself is very small. The treadmill by itself is too small to radiate effectively at, say, 40 meters or 80 meters. But the treadmill's plugged into the 120 volt AC outlet, And that outlet, of course, is fed by Romex from a circuit breaker panel on the other side of the basement. So there's that long cable can radiate. So all I have to do is keep the noise from getting to that long cable. So I made a combination common mode choke and filter. I plugged the treadmill into that combination, and the other side went to the AC outlet, and it worked perfectly. From the front yard of that house, you could not hear the noise, and it had been way over S9. Another thing that you need to know, it's number 2. A lot of devices making noise have more than one cable connected. This treadmill had one cable connected. It was the power cable. But lots of devices in your house have multiple cables. For example, a wall wart. There's a wall wart on my, I'll kill this. I'll keep screaming. I was going to hold up and show you an example, but I don't have time. I'm sitting here in the chair. You've seen me for the last couple hours with my laptop doing Zoom. And I have an iPhone, which is on the table right next to me. And the iPhone has been sitting here all day, and so I have it plugged into a charger. That's about, it's actually, I can reach it with my right arm. Well, that charger has 2 cables connected to it. One is the about 5-foot long cable that comes to my iPhone, and the other is Romex that runs through the walls and ceiling and so on to get to my circuit breaker panel. If you find the source is a wall wart, of these 2 wires, obviously the longer one that's going to radiate better is the Romex, which probably, is long enough to radiate well at HF. So what you have to do is keep the noise from getting from the wall wart into the AC outlet, into the cable. You have to, half of the time when hams use chokes or filters because they've heard they should do that, they violate the rule. My rule here says choke and or filter every cable connected to the source. And a lot of hams get in trouble with that. Let's say the source might be an HD TV set, like the one I have right here in the room. Okay, the HD TV set is actually, it can be a big noise source. That great big panel has all kinds of wires going horizontally and all kinds of wires going vertically, so that the display driver can switch current to any cell of the screen, any one of the 1080 pixels across HD, or twice that for 4K HD and so on.
Chuck, don't you have some pictures of some of these solutions that you've come up with that you could share?
I do. All right, I'll skip ahead and show you some pictures. This is all in the package, the 100 megabytes. I'll show you some pictures. Okay, there's a zillion pictures here. If you really seriously have noise problem, you should look at all this stuff, and you'll learn things such as you gotta choke every cable. All right, here's just a few pictures. I'm trying to, okay, here we go. All right. Um, this is a picture taken in my basement. I have a bunch of devices in the basement, such as a sump pump and a dehumidifier and, various things. And three of those devices are plugged into this multi-outlet strip, which cost me $1 or $2 at a Hamfest. Okay, here are the three plugs, three devices. These may be noise-making devices. Okay, they're plugged into this strip. The strip has a good LC two-stage radio frequency filter that passes 60 hertz AC just fine, but attenuates RF. And this is a wonderful filter, and I buy them by the case load because I use so many of them, and I give them away or resell them to hams who need them. But filters like this filter the difference mode of an AC line. An AC line cord typically has three wires in it, one white, one black, and one green. The green is the safety ground that connects the metal body of the device to earth ground. That ground doesn't normally carry any current, a 60 hertz current. It may carry lots of RFI, lots of RF noise current. Usually most of the noise that comes out of a device comes out in what you could call a transmission line mode, aka a difference mode involving the white and black wires. And by difference mode, I mean that when the current is flowing from right to left in the white wire, it's flowing from left to right in the black wire. That is, they're equal and opposite currents. And this happens naturally, most devices, any device, just a lamp, a table lamp or something, draws current from the black wire, goes through the device, does something useful, and then returns to the line through the white wire. This is like open wire transmission line on ham radio. It's a balanced mode. And the important thing to know about the balanced mode is that a common mode choke with ferrite or something wrapping the line cord around the ferrite won't do any good at all because it's a balanced pair. A balanced pair is self-shielding. All the current going one way in one wire goes the opposite direction in the other wire, and the wires are twisted so that one wire is alternately on the top and on the bottom and on the top and on the bottom. Ethernet cable, gigabit Ethernet cable is all twisted pairs. Okay, a difference mode filter stops that mode of current flow, but it does absolutely nothing for the common mode. And some of the noise that comes out of a device comes out in common mode. That means it flows in the same direction in all the wires. And that only the common mode current can be stopped by a choke. So you have to do both. You have the difference mode filter, which you see here, And out of the difference mode, I notice that the green wire, by the way, doesn't even go through the filter. And then the two line wires here, they're brown and blue rather than white and black, but that doesn't matter. Those all three line wires go through this vinyl jacketed line cord, and that line cord is strung with ferrite beads. That's a common mode choke. And so the noise that's made by these three appliances plugged into this multiple outlet strip does not get to the AC line, which you'll find in this outlet box over here. That's one picture. Here's another example, another picture. This photograph shows what I made for my neighbor's treadmill. This is simply a simple extension cord with a 3-prong AC, 120 volt AC plug right here, and a 3-hole female version at the other end. So it's just a short extension cord. So the lady's treadmill was plugged into the female end, and the male end was plugged into the wall outlet. Now, why does this magic extension cord work so well? Well, you can see. First, it has 1, 2, 3 common mode chokes that are multiple turns wound on a 2.4-inch toroid of ferrite. And at the other end, once again, has 3 common mode chokes. Okay, that's common mode. And then in between, here is a difference mode AC line filter. And same story. Notice the green wire, which is bare copper, or it's the safety ground wire. Bare copper coming in on the right does not go through the filter. It goes around and continues out the other side. The filter filters the difference mode, but you've got to do both. This simple device, which you can build on your kitchen table for, there's so much ferrite and so on in here, this may be $50 worth of parts, but this is extremely effective. I mean, I couldn't hear her treadmill afterwards. Here's another example. Now let's see, let's skip that. Okay, Ethernet cables. I mentioned Ethernet cables. My house is full of Ethernet cables. Yours is too. I've got, my FiOS terminal is in the basement and my shack is in the second floor. And it's a big house. So I've got Ethernet cables pulled through the wall, going up to the second floor and running from one end of the house to the other through the attic and so on. These white cables here are Ethernet cables. They are, I think these are Cat 6 cables because I did this 20 years ago. And what do you see? You see, it's 2 cables, by the way. This is a outlet that was installed in the wall behind my wife's computer table. Each cable has beads for common mode choking, and it also has a toroid for common mode choking, but there's just common mode choking, and that's because the the difference mode of an Ethernet cable does not radiate because all the pairs in an Ethernet cable are twisted, as you're well aware. And one question is, why do I have both beads and a couple of toroids in each? And the reason is that bead chokes are most effective at the upper end of the HF range, like 10 meters, say, or 15 meters, whereas a wound toroid is most effective at the low end of the HF range, like 160, 80, 40 meters. And so if I used just beads, then I would not be killing the low frequency noise. And if I used just toroids, I would not be killing the high frequency noise. This, now, how do you know how many beads, how many turns, all that? That's more of the text. There's a bunch of pictures on that. One, let's see if this is a picture. No, okay. But this is another thing. You've got to read all this stuff and learn this. Otherwise, you can spend a lot of time and money on ferrite and filters and not solve your problem. And hams do this all the time. You've got to choke and filter every cable. And a short answer to why everyone, it's for the same reason that if you have a boat and the boat has a bunch of holes in its hull, you plug every hole. Because if you leave one hole unplugged, that water will leak in through that, and you will have wasted your time plugging all the other holes. If you have a bunch of parallel running cables that are going from here to there, you have to choke all of them, every one of them. And not only that, you can't choke them just anywhere. You have to choke all the parallel running cables in the same perpendicular plane. And why is that? Well, if you choke one cable at this particular place, that's great for that cable. But if you don't choke the second cable in the same place, then what happens is RF noise carried by the first cable is coupled to the second cable because the two cables have running close together. They have mutual inductance and they also have capacitance between them. So you may have blocked the noise on one cable with your one choke, but the noise on the other cable goes right past that choke. And worse than that, the noise that gets carried past the choke in the unchoked cable gets coupled right back to the first cable on the other side of its choke. So this is another rule. You got to read all this stuff and follow all the rules. Hams, if they don't follow the rules, their noise doesn't go away. And then they tell all their friends, I tried doing what that councilman guy says. I choked all the cables and I still have noise. Well, there are all these other rules you've got to follow. Now, there are different kinds of chokes, like beads and toroids. And what kind of choke do you do? And that depends on the thickness and flexibility of the cable. For example, if the cable is very thick and stiff, then you cannot reasonably wind it around a toroid. You're going to have to use beads. Another thing is the cable may have a big connector on the end, and you don't want to remove that cable. That big connector is a lot of work, and you'll probably screw up the cable. Um, that says that you cannot use solid beads. You've got to use split beads that can be snapped around the cable. And why don't you always use split beads? Well, it's because split beads are compromised. They don't work as well. The problem is there's a microscopic air gap between the two halves. And if that air gap gets to be as big as 1 mil, really tiny, you might not even be able to see it. That destroys that destroys the ability of the bead to attenuate RF noise. And another issue, if you want to quiet received noise across the whole HF band, well, that's a bunch of octaves. It's well, 10 meters to 160 meters. It's 2 to the 4. That's 4 octaves. Usually, a choke that works well at 10 meters does not work well at all at 160, and vice versa. So you may have to do both. And you notice I did both with those Ethernet cables. Let's see. I'm just looking for pictures. I can't read all this. It'll take too long, but you can read it all. That's why I'm putting it all up. More pictures. Sorry, let's skip to next. There's a lot more, and I have a lot of pictures. One of the rules you will find if you read all the stuff is don't waste your time making a choke whose common mode resistance is less than 1,000 ohms. A common mode choke has a common mode impedance that it inserts into the common mode of the cable. And impedance is complex. It has a real part, R, called resistance, and an imaginary part, usually written X, which is reactance. Forget about the reactance. Why is a story you can read about, but I'll just tell you. Reactance is irrelevant. And one of the problems with commercial chokes, you read the ads and it says has impedance of 3,000 ohms. Yeah, it's the magnitude of the impedance, but if it's all reactance, it's false advertising. It's misleading. It's the resistance that matters. And so you'll want to know, what does a 1,000 ohm choke look like? Okay, I have pictures so you can make them. One of my favorite chokes, this is really, if I had only one kind of choke, this would be it. This choke is a bead choke, but
Can you maximize that picture?
oh yes, I'm sorry. See it now?
Yep.
Okay. This is a very clever choke. And it's my favorite choke, and I use it whenever it fits. Notice it's about 9 inches long, and the secret of this choke is that it's actually a double bead choke. It's made of 2 different kinds of beads. Here are the part numbers of them. This second bead here, 26-311-02-002, is a bead that, see this bead right here by plus sign is on? That's a 2002 bead. its outside diameter is 1 inch, and it has a hole through the center. The inside diameter, that is the diameter of that hole, is a 1/2 inch, 0.5 inches. Actually, it's 0.505. And the bead is 1 1/8 inches long. As from one end to the other end is 1.125 inches. Now, 1, 2, 3, 4, 5, 6, 7. There are 8 of these beads, and each one is 1 1/8 inch long. So the overall length of the string is 9 inches. Inside these big fat beads are little skinny beads. You could look in the space between 2 big fat beads, and you can see there's a bead inside. In the inside beads have an outside diameter of just 1/2 inch, or a little bit under 1/2 inch, so that inside bead fits nicely inside the outside bead. And then the ID, the inside diameter of the inside bead, is 0.2 plus a little inches, 2/10 of an inch. These inside beads happen to be exactly 1 inch long, 1.0 inches long. If you use 9 of them, then you get 9 inches. So the string of inside beads is 9 inches long, the same as the string of outside beads. This is a great choke. There are very few chokes that have this property. This choke has resistance, real part of the impedance, greater than 1,000 ohms throughout the HF range, from 3 to beyond 30 megahertz. And there are not many choke designs that can do that. That's a factor of 10. Now notice that does not include the 160 meter band, but it covers the whole HF band. Now, the coax that goes through this and goes to this SO239, I think, is RG303. It is very good coax. It has Teflon dielectric, and it has a center conductor, which is silver-plated solid copper, and the braid on the outside of the, and the dielectric is Teflon, if I didn't say that. And Teflon withstands high temperature and also has very low RF losses. This choke is good for greater than legal limit power at substantially non-zero standing wave ratio. So this is a pretty bulletproof choke, and I've made a lot of these. I love this. I have had one of these chokes in my transmission line between my station and my antenna for 25 years or so. And it, I don't know, it doesn't always see a low SWR, and this is a compact choke, doesn't take a lot of space. I highly recommend this, and it's good for high power, high temperature, and so on. Okay, that's one kind of choke. It's not a 160 meter choke, but it's a great one for HF. Okay, now another kind of choke you see a lot is a binocular choke. It's made with just 2 beads. And they're the same 26311 02002. There's one on the left and one on the right, and notice they're parallel. And there's no tricks, there's no concentric beads. but the cable that's wound through this is Teflon cable. My favorite cable for this is RG400, which has Teflon dielectric, and it has a stranded semiconductor. Otherwise, it's all silver plated and all the same. Why do I prefer it for this choke? Well, this choke, you see, is wound around. It's not out, it's not straight. It has this, fairly tight curve. And for a choke that's wound and has curves, I prefer to have a stranded center conductor, because that semiconductor is flexible, and when you bend the cable, that center conductor does not try to mush its way through the soft Teflon. This choke has 3 turns. You notice the cable goes through each of these cores 3 times. Comes in here, goes through once, over here, down that once, and then around here. Now there's a second pass, and then there's another second pass in there, and then a third pass, and third pass here, and it comes out. This is a good economical choke because you only have to buy 2 beads. I think a bead costs about $1.50 if you buy them in any kind of reasonable quantity. And this bead, this is a good choke, more than 1,000 ohms, but not quite the same wide frequency range as my concentric bead choke. This is from 3.5 to 29. So it gives you 1,000 ohms from 80 through 10 meters. And this is, I use a lot of these. Another kind of choke is, this is just these are toroidal chokes. This is Ethernet cable, this yellow cable, and it's wound 1, 2, 3, 4, 5, 6, 7, 8, 9 turns on this ring and 9 turns on this other ring. And just because I could, I put a bead just between the two, because it basically didn't cost much, and it improves things just a teeny bit up at 10 meters. This choke also gives you 1,000 ohms from 3 to 29 megahertz. So here's another cheap choke. It costs more than that binocular choke because these rings cost a little more than the beads. And one thing to remember is if you don't really understand common mode chokes, and I claim that very few hams understand common mode chokes, follow these recipes religiously with no deviation. I counted the turns. This has 9 turns. You might be thinking, oh, well, if 9 turns is good, then 10 turns will be better. Wrong. It'll be worse. A wound choke has the problem of capacitance between this turn and that turn, and this turn and that turn, and so on. All this distributed capacitance, it spoils the effectiveness of the choke at the high frequency end. So if my recipe says to use a certain number of turns, use that number and don't wind anymore. It'll be worse. Another rule I've just told you: make chokes that have 1,000 ohms resistance. Okay, that's good. But how many of those chokes do you need? Well, 1,000 ohm choke doesn't do you a lot of good And the reason is that the characteristic impedance of the common mode of a cable with the return path being the ground is depends on how far from the ground the choke is, but a good round number is 3,000 ohms. You can measure it. Well, think about it. If let's say you've got a matched load at the common mode is matched. There are no standing waves in the common mode. And that's an optimistic assumption, okay? Chances are you have not matched impedance for the common mode. But so, the best case is you've got 3,000 ohms without any big, pattern of nodes and loops. Well, it's a 3,000 ohm circuit. If you insert 1,000 ohms of series resistance, you're not going to attenuate the common mode current very much, right? So you have assume that you're going to use multiple common mode chokes. Each one's 1,000 ohms. Now you might say, oh, well, instead of say using 5 1,000 ohm chokes, why don't I make one choke that has 5,000 ohms impedance? Wrong. That doesn't work. You can't do it. You can't make a choke of reasonable length that has 5,000 ohms of resistance over any kind of a sizable band of frequencies. And the reason is stray capacitance. Your cable comes into the choke from the left, let's say, goes through the choke and comes out the other side and goes off to the right. Now, suppose your choke were a perfect choke that had infinite impedance. And, you can simulate that for experimental purposes by cutting 2 inches out of a cable and just leaving an air gap. That's a perfect choke, right? No current flows across the air gap. Wrong. The impedance of that air gap is probably less than 5,000 ohms. It depends on frequency. I've done this experiment, by the way. I've got data. But there is stray capacitance between the cable on the left before the choke and the cable on the right after the choke. So you're kidding yourself if you think you can put a 5,000 ohm choke in a cable and accomplish anything. I mean, even if the choke, were replaced by an air gap, which would make the cable useless, well, you'd still have common mode current flowing by there. So putting a 5,000 ohm choke in there, that choke will be bypassed by the current flowing through that capacitance. So this says that you've got to, not only do you have to use multiple 1,000 ohm chokes, but you have to separate them. And that's another mistake people make. They say, oh, Councilman says I need 5,000 ohms to solve my noise problem. So I'll put 5,000 ohm chokes in my cable, and they'll leave 6 inches or 3 inches between one choke and the next. Wrong. That doesn't work. There's too much stray capacitance that goes right around your chokes. You need to separate the chokes. You can't bunch them together. In an antenna feed line, of course, long feed line, there are lots of places you can put chokes. The certain places you absolutely should. First, you should put one at the feed point of your antenna. That's because your antenna is balanced and your coax is not. And if you don't have a choke right there, then the coupling between your antenna and the common mode of your feed line will be very high. And so all kinds of noise from your shack will be getting to your antenna. So feed point of your antenna is the first place. Second, put another second choke at the other end of the feed line where the feed line leaves your shack. Okay, it's at opposite ends. And now we've got 3 more chokes. Put them in between. Now, if you have a lot of room, this is a long cable, the ideal separation, if you can do it, is to separate one choke from the next by a quarter wavelength. Yes, quarter wavelength is different for different bands, which says that you've got to do something a little different. And the reason, so you distribute your chokes along the feed line, separating them. And the reason why a quarter wavelength is the best possible separation is that if you put a choke in a cable at one point, you're introducing a high impedance, 1,000 ohms, in the common mode at that point. If you go a quarter wavelength down the cable from there and look back, a high impedance looked at from a quarter wavelength away looks like a low impedance. So the impedance of the common mode, a quarter wavelength away, is low. That's great because inserting a 1,000 ohm resistance at a place where the circuit impedance is smaller than 1,000 ohms will be good. So your 1,000 ohm choke will do a lot more good if it's a quarter wavelength away from another choke. And after you've choked your feed line, then you should choke all the AC power cables to your shack, because the AC power network in your house is the noisiest thing around because all your noise sources are connected to it. And the same rules, you should, put chokes all around your AC network. And AC power network, but you've got all kinds of other networks, long cables running around your house. You have telephone cable, you have data cables, in other words, there's Ethernet. You'll have HVAC, you've got thermostats controlling your air conditioning, controlling your heat. Those are more cables. You've got a security system, alarm system, windows and doors and everything, and cables come back to the box controlling your whole system. Then you've got rotator control cables, remote switch, etc., etc. Every other cable entering or leaving your shack needs to be choked, because if you leave one unchoked, then all the noise will come in that way. I think I've gone long enough.
Yeah, Chuck, I agree. You've been talking almost 2 hours now. You must be getting tired yourself.
Yep.
So what we could say is we'll endeavor to get this slide set up so that the club members can access it, and then if they have specific questions, they can approach you. How's that sound?
Yeah, if you read everything, then you won't have any questions. It's 100 megabytes of stuff.
Okay. Very good. So we're way over, but are there any questions for Chuck at this point?
Jack Schuster put a question up that appeared on my screen briefly and then went away. So let me answer that. He said something like, make sure he mentions that he choked the copper water pipe to his house.
Mhm.
Okay, I mentioned cables, but any conductor, like a pipe, that carries noise too. And in my house, my washing machine had a variable speed motor, was a terrible source of RF noise, and your washing machine is connected to your cold water pipe and your hot water pipe. And I found when I actually measured, there was more noise current flowing on the hoses that gave water to the washing machine than there was on the line cord of the washing machine, because I had choked and filtered the line cord. So then I choked the hoses. I
That's
could
pretty
hear noise
crazy.
all over the house until I choked the hoses.
Yeah. All right. Oh, I see John has a question.
Yeah. Hey, Chuck, we are very familiar with your Belmont station, but can you give us an idea of what you got for antennas down there in Connecticut?
Sure. I have just wire antennas. In Belmont, I had just one wire antenna, which was this multi-band. Okay. But I had to do that because in Belmont, the only space I had was 70 feet between two pine trees beside my house. But in Old Lyme, I have a much bigger backyard. So I was able to select two trees that were about 180 or 200 feet apart. So I thought, wow, finally I can put up an efficient 160-meter antenna. So I did. I put up a full-size resonant, self-resonant, it's called a Lazy H vertical. I got the idea from Don Toman, K2KQ, but I didn't invent it. It's a vertical antenna. It's a vertical wire, I think it's about, I don't remember, maybe 35 feet high. And then at the top of the vertical, a wire extends out in both directions, so that the total span is around 180 feet. And at the bottom, same thing, horizontal thing. So it looks like a letter H over on its side. Okay, so here's the one long leg of the H, and here's the other long leg of the H, and there's a vertical between them. That's my 160-meter antenna, and it's wonderful. Now, it's wonderful. I worked ZL by long path with that antenna.
On 160?
160.
Son of a bitch.
Yeah, that's right. And it was during a contest, and I looked at the results of that contest, and in the whole USA, I think there were something like only 3 other stations worked that station. But I could hear. Now, I got a better antenna, but still, I had to do a choke and filter job on my house in Old Lyme.
What do you use on the higher bands?
Okay, higher bands. For 40 through 10, I have one antenna that is good. I don't think it's anything super special, but it's good. I've got pattern plots and so on for it on all those bands. And its basic configuration is it's an inverted V. The top is at 50 feet. And you know what a V does. But each one of these side wires is not a single wire. It's a bunch of wires. There is a long wire that's gives me half wave resonance on 80 meters. And then there's a shorter long wire that gives me a half wavelength on 40 meters. And then the trick is each of those wires is not a single wire. I just said it was a single wire for simplicity, but it's a pair of wires spread. And the reason for splitting it is to make it lower Q, which means it's easier to drive, off resonance. And and then I feed it with open wire line.
Wow.
Because in my house, the other end of the open wire line, I have an antenna tuner, and I can match that antenna on every band 40 through 10 meters. Now, the one trick is that open wire line is common mode choked. And between the feed point and the house, there's about 5 common mode chokes inserted in that feed line. Now, there's conventional wisdom that's wrong. It says you can't choke an open wire line, but that's not true. My chokes are actually quite good, and each choke has a bifilar winding that is 2 parallel wires. They're well insulated because there's a high voltage between the 2 wires. And the chokes are binocular chokes, and with just a few turns so that they work in the range of frequencies. And this is important to decouple the antenna from the line, which goes into the house, because I don't want, in the house that's where all the noise sources are, and you don't want common mode noise traveling up the line to the antenna from the house.
Well, thank you. That's a pretty comprehensive description.
Okay. Sorry. Okay. Just wanted to point out, maybe share with the club, if you really have a taste for more of this right at the moment, go to our webpage. I'll show you in a moment. All right, I'm going to stop your share, Chuck.
Oh, I'll stop my shares.
Yeah.
Oh, let me stop my share.
That's all right. I can take it over.
Okay.
So if you get the webpage, under articles, under cargo articles, the precursor, actually the seminal document that started all of this is available on the site. Some of this data will update that document, but a lot of its core content still is pretty accurate. So it is available there. Well, 42 pages of it. So you can have a look at that while we figure out how to put the rest of this stuff up on the website. All right. Any other questions? All right. Thank you all for those of you that stuck it out. Thank you.
Ken, Fred here.
Fred.
We saw pictures of 3 to 30 megahertz chokes and 3.5 to 29 megahertz chokes. What about 1.8 to 2?
Oh, great. In my package of stuff, there is a a photograph that's labeled with lots of arrows and a lot of detail for building a real good 160-meter choke, and it's better than any other 160-meter choke you've ever seen. And I mentioned that W1IMD returned his DX Engineering chokes, and what he replaced them with, because W1IMD is, some of you probably know about it. It's an amazing station. He has a tower that's 300 feet tall on top of a little mountain. And that tower also has big, up at a height of, oh, I forget exactly, 200 and some feet. I have the details here. He put up a horizontal steel I-beam that extends out horizontally in both directions. Its center is on is at the tower. Okay, that's something else.
That's something else. It is something else.
Yeah, well, okay, all right. Let me not get to that. That's another story. That's another joke. You should be able to find my dynamite 160-meter choke in. I can find it if you can't. It's in the package up that I gave you. Oh, and yeah, those are.
Is it this one? Hang on. I'll share it one moment here.
Find it?
That one you're talking about?
Nope, that's not it.
That's not it.
I got a lot of amazing chokes that do amazing things in here. And there's a story with every one of them, and I could bore you for a solid month.
Not that one?
No.
This is labeled OWL low band choke.
Yeah, okay, all right. So while we're here, this is a choke for a balanced line. This is a choke. I mentioned K1ESE. K1ESE has two very high wire antennas. He's got some huge, really tall trees on his lot, and he feeds them, but they're way back at the back of his lot. There's a long distance, and the only reasonable way to feed these things, coax would have too much loss. So he uses a balanced feed line. So, and he wanted to choke his balanced lines. He had two lines, and one of these antennas I think he used for the high bands, like, I don't remember, 2015 and 10, and the other one he used for the lower bands. And this is the one I made him for the high bands. And this picture has some interesting features. First off, you notice that it's bifilar, okay? Another thing, you notice it has pretty thick Teflon insulation. That's because there's high voltage on this wire. And then that pair of wires is wound, looks like maybe 3 turns on this core on the left. And the core on the left, that's a pretty big core. I would have to look in my notes to see what the ferrite part number for it was. And then one of those chokes doesn't have enough resistance, so there's a second one. And there are some ceramic spacers here, and their only purpose is to maintain the spacing of the line. But what you're looking at is, this is an example of how you can choke a two-wire line, a balanced line. And I've choked a whole bunch of balanced lines for 160 meters through 10 meters, and one of them belonging to WO1I, that's Dicklin's and in Newton. I choked a big wire antenna for 160 meters, and that was done I think it was more than 10 years ago, and that choke is still in service. And the standing wave ratio is high, and he transmits high power, and you know, it rains and it snows and all that, and that choke has never failed. So you can choke open wire lines, contrary to what you might, or well, I have read certain places.
Okay. This choke that we're looking at does list greater than 1K from 1.8 to 18.
Yeah, that choke, okay, this, Ken, you know, but everybody else should know. This paper that's on the screen right now is really old. There's a date, I can read the date in the footnote
2006.
number 1. 2000, that's 20 years old. And part of me wishes that I could delete all copies of that paper, because in 20 years, I have developed so many better designs that, but I can't ever get rid of this paper, because it's on websites around the world. It's on the YCCC website. I actually had it removed. I got the webmaster to remove it from the YCCC website years ago because it was obsolete, and it's back.
It's back.
It is on more websites than any other paper I've ever written. At some point, I went to Google, and in the search string for Google, I typed, it was a real simple search string. It was something like W1HIS common mode chokes. And Google returned 22 pages of hits. That paper is not only on websites everywhere, every ham club in the world, but it's translated into more languages than I knew existed. A whole bunch of Asian languages that use non-Roman alphabets. Okay, I mean, it's a shame. But my favorite choke was the concentric bead choke. It's only 9 inches long, and it's so good. I hadn't developed that back then.
Right.
Another problem back in 2006, my favorite material, which is Ferrite Products material number 31, that material was brand new and in limited availability when I wrote that paper. So I think I remember that mix 31, it may not even be mentioned in that paper, but and in those days the best available mix was 43. But
Yep.
anyway,
Yep, the 31 and the 73 are relatively new additions. I remember when they were
yeah.
introduced when I was in my professional career, and we jumped all over. We had a specific problem, and I think it was 73 really helped us out. So
Yeah, that basically almost everything I do can be done with mix 31 for 80 through 10 meters, and actually 6 meters. Actually, it's even good at up at 2 meters, but and then for 100, however, for 160 meters, you get much more bang per buck out of mix 73 or 75 or 77, which are very similar, except that apparently there's a manufacturing problem such that Ferrite Products uses mix 73 for large parts, like 2.4-inch rings and big beads and so on. But for small parts, like little beads, it uses the others, 75 and 77. Apparently, they're cheaper to use these others for small parts.
yeah. Okay then. All right, I think that pretty much wraps it up. Thank you again, Chuck. We'll be talking over the next few weeks. And with that, any other comments or questions about the club in general?
Don't miss the NA sprint tonight, 7 o'clock to 11. CW 80, 40, and 20.
Oh, wow. Sprints are mind-blowing contests, so I tend to avoid
Make
them.
sure you look at the unique rules.
Yep. Okay, guys. Ladies and guys. I'm going to wrap it up here. Unless there's anything else. Thank you. Thank you for sticking around. I appreciate it. With that, we'll wrap up the club.
Thank you all.
Thank you.
Motion to adjourn.
Seconded. All in favor?
Aye.
Thanks. Thank you, Mark. All right,
Thanks,
take care.
Chuck.
Yeah.